However, there is a problem of physical units. You need a constant to change from one physical unit of the field to the current, to a current. There is a constant, a Taylor-Scanlon factor.
What is constant, sorry?
The Taylor derivative of the electromagnetic field leads to the currents, but there is the physical constants, the electric permeability and the magnetic.
Can we make it equal to 1? I'm asking.
You take equal to 1? No. Depending on the system of the units. Okay.
It's
It's
a matter of how we define the current.
Okay.
Well, maybe because we are out of time, I should. You're going to talk about harmonic functions later.
Well, okay.
So maybe I should use the Laplace.
Well, perhaps it is important to develop the Laplace within the Keller calculus so that there are 4 terms. Because in the literature they put only two terms, but that corresponds to scalar value differential forms.
So if we define it like this, but this is not only in Keller, this is the whole Laplace of Laplace, right? So we define as d plus delta square, which of course has 4 terms. Plus d delta plus square. For functions, of course, for scalar functions, we have t squared plus 4. We have
Same thing.
yeah, delta also. Of course, if d is equal to 0, delta is also going to be equal. Delta square is also going to be equal to 0 because this is nothing but z squared conjugated with the Hodge operator. Okay? So, yeah, in the case of scalar functions, can I use this notation?
I don't know what you're referring to. Now, the next step, that is for a scalar value, but now if you make it f, then the delta f is 0 and you only have 1 term. See what I'm saying?
Yeah. Very strong notation. Yes, of course. For a scalar function, delta is 2, 0, yeah. So we're going to have delta d, nothing more. Which in Cartesian coordinates is written as the divergence of curl.
Yeah. Is equivalent.
So this is in Cartesian coordinates. For scalar value function. Okay, so maybe you're going to talk about the Cauchy theorem and the decomposition of differential forms.
The what?
Cauchy theorem and the decomposition of differential forms.
Well, I guess that with the time that there is no time for that, it is an application which is, one can mention it.
Yeah.
And I would ask Professor Acampo to read my paper and tell me what are the conditions under which that construction works. Because I'm not the person, to decide on those issues when I have problems to remember what clause to what, all those concepts. But people with your knowledge of Professor Rosiewicz could read that and say, this works under these conditions.
Yeah, but the reading is difficult because lack of definition.
No. You can blame that, yes, but then take the Keller paper, you know German,
Yeah.
it is written by Keller, not by a poor idiot like Jose Vargas, okay? It is written by Keller, and therefore you should be able to understand and then translate into a rigorous language. And right now, apparently, people start by not understanding the paper, okay? So that if they understood, they could improve the language. I have tried to improve it a little bit by writing it a la Cartan, which is my Bible, okay? But Cartan still is not, the language is not modern enough. But if you understand Cartan, unfortunately, people do not understand Cartan either. But what I'm saying, that is not a job for me. I'm a physicist. I think I'm advanced enough that I can speak of those things. You're not going to find many physicists that speak of physical bundles and that speak of chemical.
I would suggest you try to make the most economic introduction.
Yes. Well, I mean, I don't know, okay? I'm not a good economist, okay? Maybe after what you have heard, and if you read the Keller papers, you can do it yourself. Incidentally, I think that the lecture of Professor Osiewicz, with whom I got mad, it is most sure was probably very, very, very interesting. Okay?
It was extremely interesting.
Yes, yes. My only objection that it was not the right time. If he does that at 5 o'clock, wonderful. But we have to reach certain formulas. Okay.
There are enough, in this week I have seen enough formulas.
No, well, that...
So when I look to what I eat, I would say I have...
Yes, but that is from the perspective of your interest. The point is, quantum mechanics...
No. If I see a formula, which I do not understand, and slightly later I see another formula I do not understand, I can't stand
I understand.
1 or 2 hours.
Yes, that is why I'm asking you to start from the beginning and translate it to your language.
No, we use the same language. We use the same language. Exactly the same. So there are many things which appear on the blackboard which I recognize immediately. But if you write in straight English, without that...
Because in order to connect with Keller, I'm using fewer indices than Keller, but I don't know how to use fewer. Because if differential geometry is theory of moving frames, if we use frames, at some point and we change frames, okay, it is convenient to use. Anyway, we are wasting time, I think.
We need to go slowly. And it seems to me that patience is something which is very rare. My children, when they are not patient, I will tell them in Basel there is a shop, you can buy patience.
At the table, somebody said, I think it was Professor Fiorini, that what it is being attempted to be done is already far too much, true or not. And if we go more slowly, okay, which I might not be able, okay, if we go more slowly, we are not going to reach to the big thing. That the foundations of quantum mechanics are going to be totally different if we use the Keller calculus. And
it's like multiplying. If you do not go fast, you do not reach the top. But if you go too fast, you die,
listen,
you go reach the top.
Okay, when I go up the stairs, I get bored.
That's why my case.
When I go up the stairs, okay, one by one, I get bored. Okay, and I have to climb them in twos. And it happens that I can beat almost anybody at 71 years of age. So what I'm saying is there are much of it which depends on our personality and our interests. Why don't we continue?
Yes, I was not about patient. And now I become slowly more patient.
Okay. Shall we then continue to finish the chapter?
May I just add one last sentence?
Yes.
To make the mess complete. So, because obviously we cannot decide on the egg and hen problem, I feel that at some point people should work more for a fundament and then to go deeper into
Yes.
because maybe right now we are all still young and need more fundamentals. And to make things worse, I would ask this question. Okay, there are people here who are specialists in many things. Let's say differential geometry. If you take the Koch Laplacian, this one also the Keller Laplacian, more or less the same thing. And if you take the Laplace rectangle operator, you get different things, right? They differ by...
Do you mind reminding me? I always ignore this one. Do you mind writing it down? Deriving
second order differential operators.
Well, I don't remember Beltrami. I knew 20 years ago.
Working with the illustrator connection.
This kind of, if you use Christoffel derivation, discuss also scalar curvature.
Yes, exactly.
This is Bochner making for the A. Bochner makes it much better than Kerr, much better.
Thank you. I feel that this should also be explained even a little to others because no, I'm not. I won't feel comfortable to talk about this because I'm trained. But I think in further lectures maybe we should mention this type of Laplace operator. They're both called Laplace types of operators. They differ in terms depending on curvature. Also
the curvature is there. In currents, the curvature is there.
Yeah. Okay.
In current, the curvature is there because
it is, but you get with the different approach, you get the different.
Well, the point is whether it is approach or something else, because you've written, okay, not equal, and not equal, for me, it means that it is not only a matter of approach.
Definition. Well, there are different Laplace operators, obviously. There are two of them that are very popular.
Well, yeah, but one have to be careful, because what happens in that, you could see Laplace
You also get
as just this, or as that, depending on, depending on the situation.
Yes.
So, but normally, very rarely you go beyond that.
Yes. For this case, it's just scalar curvature. Of course, you have this type of thing also for the Dirac operator. You have Lichnerovich, Weissenhoff,
But Bochner was the...
Bochner type, yes, formula, but for the Dirac operator. It's just a different...
Okay, so now I think then it's time to start speaking of, okay, high idempotence.
Yes.
Okay, and constant idempotence.
Yes.
Okay, and because that is going to allow us in due time to connect with the Dirac theory and show how Kerr is infinitely superior to Dirac. So connect here.
You need...
No, I do it here.
I'll just do it.
The other one is not to afford. The one is C. Okay. It is as the Kerr equation, which then I think is good to start to become clear with it, has this form. Where U is going to be the scalar value differential form. Kerr also then gives some theory, potential value differential forms, but he has a very complicated equation for tensor value differential forms. In fact, such that, okay, the number of, if you have here are indices, here you have R 2 R subscripts and 2 R superscripts, something like that. Double number of indices here as in there. It is, he didn't do any application whatsoever. In due time, I'm sure that the natural thing is to have Clifford value differential forms, so that the structure in which we should be interested is in the tensor product of the Clifford algebra, tangent Clifford algebra, with the Kellerian scalar value differential form. Incidentally, we said before that we have three series of indices. Remember the curve object, for instance. But when we have a metric, what did Cartan say about instead of talking about one dimensional valueness, he said that the curvature was a bilateral value differential form. So that he was already, okay? Stop, you gotta stop talking about the covariant field vector fields and incorporating them, okay, as dot products with tangible vector fields. Okay, where was I? I didn't this. The equation of Dirac, I said this for this form, and this is a scalar value input for a particle of mass m in electromagnetic field and charge E in electromagnetic field up to the constants. This would be m plus E up to the constants of the unit imaginary and things of that sort. Now, this is very Dirac, very different from Dirac, because in Dirac, the animal here is a spin. Now we know that a particle, to describe a particle, we have to give the mass plus mass plus energy in the spin. Some people will tell you spin is very closely associated with chirality. This is extremely interesting. Now, in any system of differential equations where ordinary or partial can be written as a stereo system, the expert of the stereo system was Cartan and then came Keller. Okay? And therefore, it is very interesting to hear about this from high authority. Okay? If we have a proper value of energy, then we write the function in quantum mechanics that is a proper value of energy with e to the minus I e h bar e divided by h bar. And if it is a proper function of angular momentum of the spin, we also have here e I think to the minus 1, I'm not sure. And angular momentum phi divided and is not divided by h bar, whereas in the physics it is. And here is something extremely interesting. In the physics, okay, when we study quantum mechanics, we take the operator r multiplied by the operator momentum and say, aha, this is the operator of angular momentum. This is, there is an implicit assumption of the particle being the most fundamental thing. Whereas, in Keller, the most important thing is that not RE, not the particle, but his approach to angular momentum is this, where phi is a rotation. And from there, he obtains a fascinating story about angular momentum, which you don't find anywhere else. Starting with the derivatives. Okay. The idea is the following. I think in order to go from Keller to Dirac, to the extent that they have something in common, I have to define some concepts like constant differential. Okay, first of all, I will have constant function. And you will understand the logic here. Constant differential, a strict harmonic differential, finally, harmonic differential. This is characterized by, of course, this is characterized by in constant function unit. Now, something could be this, even on a record. Something could be like this, a strict harmonic, but not be a constant differential. In many are called a constant differential. Because what will happen is that, say, assume this is a function plus a differential form, and we will write alpha sub 2. Then, if I obtain the Keller derivative of this animal, only the stereo differential part comes. And of this animal, only the interior comes. So I am going to have a one form and another one form, and they will cancel each other out. When that happens, the components satisfy the Riemann-Cauchy-Riemann conditions. So, and this is also extremely interesting for a PhD thesis. Because then, these in 3 dimensions, okay, it's going to be the Cauchy-Riemann conditions. And Cartan and Keller developed, okay, the full form of the solutions, I mean the whole set of solutions U, which is extremely rich. Anyway, I am getting distracted because there is so much here. What is a constant differential when this happens? In general, if I have dx mu for some dh of dx mu, in general, that is different from 0. But if the coordinates are Cartesian coordinates, then that is 0. Hence, any polynomial on the differential of the Cartesian coordinates is a strict harmonic. No, it is a constant differential. Okay? So, now what is not correct speaking?
This, if dh is Christoffel derivation,
dh, you insist on Christoffel derivation form.
Is covariant? Is covariant?
That is the covariant derivative.
So u is arbitrary, and dh depends on u. This is a condition for covariant derivative, not for u.
Alright, one second. First of all, I'm talking here about the covariant derivative of Keller, and I'm repeating like a parrot Keller.
But this condition, covariant derivative of u is 0, is condition for covariant derivative, not for u.
Who is saying
U is arbitrary.
the idea is you have a metric.
Yeah?
You have a metric. Assume you have a metric. Okay? And you have a metric structure.
There are infinite many covariant derivatives. Infinite many. And if
This
condition...
is metric dependent.
What?
The covariant derivative of Keller is metric dependent.
It's dependent on many things. Still.
No.
Still it depends on...
Okay, we don't have this, you know,
What is H?
Pardon?
What is H?
The H
Oh,
or
no, H alone. H alone.
H is H.
Yeah.
It's an index.
The direction.
It's an index.
Yes. Okay, because remember
It is a derivative,
that
not a differential.
define his derivative as
It is the direction.
It is a direction.
The direction of the
So it is vector.
Yes.
H is a vector.
in certain way.
So it is the direction of the derivative in the direction H.
In the opposite direction.
No.
Because it contains an additional term.
Plus an additional term. I see. And the additional term is plug in the vector in the differential form.
The additional term depends on the Stoffel symbols. And the question was, pardon me?
So do I need a vector in the point or do I need a vector field?
Use any differential
So
form.
is it a majority? Can I compute this as one point or do I need the whole vector field?
No, we need direction to compute the derivative. We need direction.
You need vector field. You need the vector, not only a
Directions of the differential forms. The differential forms have directions.
So this is something that is invariant.
It should be invariant, this directional derivative. Compute it with one coordinate with the other in the same direction, it should be the same, if I have understood.
Okay, so, I don't know why I wrote that. In any case, a constant, for instance, related to space and time, if I am to flat space-time, then the dh or dt and all the other coordinates also is zero. Okay? When I write something as an exterior differential form, and the differential forms are some exterior differential products, exterior differential forms. When I write it in that way, one applies the theory of Schrödinger differential equations. I'm an expert, but I take the word what I can. So instead of having like in quantum mechanics just the phase factor, when I have a symmetry, say time translation symmetry, okay, the solutions have to be of the form, okay, some differential form, the term I h bar h e t divided by h bar times and if in addition there is rotational symmetry, because we need both symmetries and particle, okay, we assign to it rest mass and speed, in addition to those factors. Okay, now, okay, here, this u is not going to depend on t and on dt. Only dependence on t is here, and the dependence on dt is there. If in addition, okay, I have rotational symmetry, I must have also the factor m5 times 1/2 1 plus minus I dx dy. The I is necessary because the square of dt is -1, and we need to have +1 in order to have an idempotent. So this is an idempotent, and it is constant. It is a constant idempotent. This also, the products are also constant idempotents. And it happens, I will not go into details, it is easy to prove, that if I have partial of UC, where I use C to refer to a constant idempotent, then this is E and partial, I said partial, but that don't mean partial. I mean, because of the symbol, it's easier to say. When I have Keller derivative, if Keller derivative satisfies a u, if I have this equation, the Keller equation, then it happens that this is equal . So it happens that u ideas, complementary ideas, and any member of the algebra can be composed into a subgroup of two objects belonging to each of the ideas. And now we start the same operation, and between this and that, they can split the algebra into 4 complementary ideas. And what? And the members of those ideas satisfy the original Taylor equation. So if I have solutions of the Taylor equation which belong to the algebra but not to the idea, I can find solutions that belong to the ideas. Spinorian solutions. I should have prepared with the Spinorian because it doesn't suffice to belong to, say, an idea defined by this. In addition, when I do the decomposition of a U is equal, let me call this epsilon plus minus plus, and let me call this tau plus minus. So one I can decompose as epsilon plus tau plus epsilon plus tau minus plus epsilon minus tau plus epsilon minus tau minus. If I left the multiply by any element of the algebra, I have this. And since these are constant idempotents, if the U are starting with is a solution of the Dirac equation, of the Taylor equation, all those also are solutions of the Taylor equation. For reasons that I will not enter at this point, we have here the epsilon plus, positors with both helicities and the electron with both helicities. That's the beginning of a very interesting story, but maybe I can say perhaps a little bit more, but I won't have time for questions. So, question, hit, try to hit me. Not literally you, okay? But I'm saying bring your best objections or ask your questions. Okay, at this level, forget about the mechanics. Now, if it happens all incidentally, assume that one cannot have these idempotents, epsilon tau, are primitive. I will not go into details for okay? And yeah, I cannot go any further because they are primitive. So I could continue decomposing these, but the new ones will not be primitive. So primitive is stop there. But this is because I'm using the algebra of the scalar one differential forms. Assume I have the tensor product of a tangent algebra in one of differential forms. Then the richness is absolutely fascinating. And the role of the I dt is of square minus 1. What happens is that when one develops, I don't remember at what moment, the theory a little bit further, I don't know where. This I should be replaced by E0. And this I should be replaced by E1, E2. Which are dual. And what happens? I need the unit imaginary because this is imaginary. Yeah, because E0 is imaginary enough, and E1, E2 is imaginary enough. We have a square minus 1. So one can do particle physics, and this is absolutely beautiful. Because one of the conditions that one obtains is that dx does not commute with dt. But dx, okay, if I instead of having e dt, I replace it with d0 dt. I dt does not commute to the d, the I doesn't do anything in that regard. Okay, I mean no yes. dx does not commute with dt. But when I geometrize the I, then it happens that, okay, if I have E0 dt and if I have E1 dx, these two do not commute, these two do not commute, but these products commute. So, now when we have clifford value differential forms, we are going to have all sorts of opportunities. Not only that, I could have in this decomposition okay, we have that the unit equals epsilon plus epsilon minus. But instead of writing epsilon plus epsilon minus, I could write epsilon minus of plus epsilon minus. Now minus, because the sum of those two is 1. And if I have more opportunities, I can still decompose this further and further and do all sorts of combinations, like go with those in one direction, with those in another direction, and create all sorts of chemical, okay, like if they were chemical reactions, particle reactions, provided that we identify the different idempotencies possible in the algebra. Okay? We identify them with particles. Can I start with that? Unfortunately, this is not in the 1962 paper, which is almost complete except for this type of discussion. And if there are no questions, I think that for the moment I should stop there. But you see the tremendous richness that there is in this concept. Thank you very much. Something dear to discuss. Well, you don't want it to be, but I just like to give an idea how you can use an approach that is related to this one, but is completely starting from a different assumption, because we here start from the classical assumption that we start from a top-down point of view using classical analysis tool and a continuous support just to express our information content of our problem and to find a solution. I try to show you that there might well be a complementary approach so that instead of starting from the top, start from the bottom up and start from the discrete approach and try to find a connection between the two that can give you the possibility to have a more stronger solution to real problems. I don't know if you are interested in this kind of presentation. If you are interested, I can give further. Otherwise, you are free to go wherever you like. So, what is your? I like a lot of interaction with my audience, because I need feedback just to focus on the topics that you can be interested most, just to save time for everybody. Please.
We can start and we can escape while we are.
Yeah, as soon as you're tired, you just go away. Okay, perfect. This is a natural approach. I need just a few seconds to make my computer alive.
Too tired, maybe. Need more coffee.
You can use this one too if you have it on flatline.
I need to follow this cookie because there's a lot of video on a few presentations around the different conferences. Now I try to select this particular specific topic from one presentation to another to give you, try to give you the whole story in a very short time.